let's start. So just thanks for coming today. So this is the second webinar. So the first time we look at the overview of the WASH in emergency and had an introduction to Red Cross and Red Crescent tools for disaster response. This week we are going to look in more detail into the WA of WASH, water supply, and specifically what we call bulk water supply. That is when we are looking at providing a large quantity of water, usually treated at one site for a large number of people as opposed to household water treatment. In this first presentation today, we are going to look at water source and site selection, and in the second presentation at water treatment. Recapping briefly from last time, we covered that the health of survivors of the natural disaster can be at high risk from communicable disease related to WASH. Therefore, to break some of the disease pathways we saw in the HEF diagram, the availability of sufficient clean water in the immediate aftermath of a disaster is crucial in order to provide for human consumption and maintain basic hygiene. In addition, the lack of water and water facility often adversely affect the dignity of those caught up in emergencies. One of the points we have also covered last time was the quantity of water is important for hygiene, not just the quality, so it is worth noting again that there is more benefit gained in terms of health and convenience from supplying large quantities of reasonable quality of water than small quantities of very good quality water. However, the aim should always be to provide adequate quantities of good quality water. We take into consideration relevant guidance such as the SPHERE standards and National Drinking Water Standard or WHO Drinking Water Guidelines, but we also use our experience, judgment, and common sense. For bulk water supply, we are usually looking at the water supply chain like this. On this presentation, we are going to be focusing on consideration for selecting a water source and setting of water treatment equipment as well as distribution. It's important to note that we are assuming that initial assessments have shown there is a need for a bulk water supply intervention. That is that people do not have access to enough safe water, and we will be able to provide access to them through a bulk treatment setup. When we say water source, what are the possibilities? If we look at this diagram of that shown part of the water cycle, we can see that we have a number of places that we can find water sources. When it rains, we will have surface runoff that can sometimes be collected in ground catchment. Rainwater can also be collected in household catchments through roof gutters and tanks. Rainwater also soaks into the ground, where, depending on the geology, it might emerge in springs or collect in groundwater reserves that we can access through boreholes or wells. Rivers and lakes are also fed from rain, surface runoff, and groundwater flows, and we can take water from those sources either directly or by making infiltration wells in the riverbank, which improves the quality of the water by filtering the open river water through the soil. So broadly, we talk about three categories of water sources. Rainwater, which is uncontaminated until it comes into contact with contaminated surfaces. Groundwater, any underground source, which can be contaminated or clean, depending on how well protected it is. And surface water, which is any water source sitting above ground and is always assumed to be contaminated. So which water source seat to choose? That is assuming you have choices. Let's imagine a disaster just occurred. People are displaced. Water services have broken down. There is a need to help people with water supply. Basically, we have 4 main criteria to consider. First one is the quantity. Can the source provide enough water to meet the needs of the people we are trying to serve? Second is the quality. Can the source provide water of sufficient quality to meet our needs, or do we have equipment that can treat this water effectively? Third one is access. Is the access to the seat feasible for people and equipment, and is there permission to extract water from the source? If others are already using the same source, how will it affect them? Safety. Can we keep people working at and assessing the seat safe? Will equipment be secured? Which of these 4 characteristics do you think is the most important? I give you a few seconds to think about it. Okay. I'm not sure we can say any one of them is more important than the other, but depending on the context. You might weight this differently. Each of them needs to be considered carefully in making decisions. One thing for sure is that you rarely find a perfect source and a location. Let's take our first criteria of quantity and go back to sphere for some guidance. Why do we strive to deliver more water than just for drinking? If drinking water supply is low quality, waterborne disease such as cholera, typhoid, and dysentery, but also when people don't have enough water, they stop usual daily activities such as washing, bathing, cleaning pots and pans. These poor sanitary practices lead to poor hygiene, which combine to increase the risk of water-related disease. According to Sphere Water Supply Standard number 1, we need at least 7.5 liters per person for the first phase of a disaster. Then moving on 15 liters per person at the earliest possible time. When we talk about quantities of water needed for domestic use, it is very much context specific. It may vary according to climate, available sanitation facilities, people's habits, religious and cultural practices, food that they cook and eat, etc., etc. Therefore, 15 liters per person per day can be exceeded to conform to local standard where that standard is higher. Some of the additional questions to consider: is there equitable access to water supply? Is the quantity from the source reliable, and would seasonality affect it? Does provision for water for livestock need to be considered? The second one is access. The geographic location of affected population. How far are the water collection points from where people live? Any other possible alternative sources? Road conditions? Road conditions, for example, can a water tanker truck pass through? Can I use access a warehouse? Is there enough suitable space, like flat, stable ground for treatment and storage equipment? Are there any legal or other obstacles to using the existing or new sources? Participation is also part of access. Participation of local community is critical. Consider whether it's culturally accepted, think of ownership, and how you can get those affected involved in the process sustainability of your services. Beneficiary participation is a key. Beneficiary must be consulted at every stage. Don't forget, a beneficiary population contains a usual cross-section of society. They are a resource with local knowledge and skills. Water quality, as per the sphere standards, is defined as water that is palatable and of sufficient quality for drinking and cooking, and for personal and domestic hygiene without causing a risk to health. Some of the standards that we aim to adhere to during emergency include less than 10 fecal coliform units per 100 milliliters of water at the point of delivery, when we are talking about unchlorinated water. So this standard is a new standard. So this is different from the previous standard. 0.2 to 0.1 milligram per liter free residual chlorine at the point of delivery for chlorinated water. A turbidity of less than 5 NTU. Protected treated water source preferred over other readily available unprotected ones. Please note it is also mentioned about maintaining the water chains with no contamination between point of distribution and point of use. This including safe collection and storage at household level or household level water treatment and safe storage. We are not always in the position to do a full range of water quality testing and monitoring, but we can undertake rapid sanitary surveys and implement basic water safety plans as risk management tools. Guidance on both these tools can be found in WHO drinking water guidelines, and we'll provide some links in the resource on the website for this week. But remember, all surface water will be contaminated, and if surface water is being used as the source, it should be treated including disinfection. Different treatment units might also have different water quality parameters, like turbidity, which affect how well they can operate. We'll cover more of that in the next presentation on water treatment. If there is a likelihood of industrial pollution, those risks should be rapidly addressed by carrying out a water quality testing analysis. If there are no other options, you would want to seek expert advice to make a decision that balances short-term public health risks and benefits. Palatability or the acceptance of test is not a health problem in itself. But if people choose to drink unsafe water over a treated supply that does not taste good, which can happen, for example, when chlorine is used with people who are not used to chlorination, then health problems can arise and hygiene promotion activities are needed to complement the water treatment. In terms of drinking water safety that was covered under quality, here we are talking more about safety and security at the site, which is often context specific. We may have to consider physical safety from natural hazard, for example, aftershocks from earthquakes or floodings from continual rains. Consideration of the political context. Is there going to be any safety concern for staff or equipment at this site or from using this source because of who controls access, or will it cause additional pressure on host population? Is it possible to fence the site, store any chemical consumable safely and out of reach of animals, children, and curious adults? Are there likely to be problems with theft? Will byproducts be produced, like settled sludge from water treatment, and how will they be disposed of? Make sure correct permissions are obtained and it is well explained what will happen on the site and how long it is likely to be occupied. Staff operating equipment and handling chemicals need to be properly trained and supervised. Now, having looked at some of the key consideration, where can we find information to help us make decisions. First of all, secondary information. Some of this information can be gathered even before arriving in the affected area. Use the WASH cluster if it is existing. They will have information and contact to share. On-site information collection. Catchment mapping involves sketching of all features in a catchment area and can help indicate potential sources of pollution from population upstream or from industries. Local knowledge regarding sources is vital regarding options, seasonality, permission for use, water quality testing information may be available from local utilities. Information about agriculture or industry in the area can give some indication of contamination risks. Health information can also give some indication of the situation when put together with information about water source. Ask as many different people as possible in the time frame to confirm answer. Sanitary survey observation can investigate local vicinity of the source and risks of fecal pollution. These risks relate to present and future scenario. All surface water sources will fall into the high risk category, but the questions should still be answered to identify which of the risk factors are present or which can be improved. And you can also do water quality analysis. Give single result for that moment in time. It's indicative without information about all parameters. Some parameters, such as fluoride, will not fluctuate over short periods of time, but others can, such as turbidity or fecal contamination. Measurements of turbidity and salinity are often taken with field kits to help decide the applicability of different types of water treatment. We will see that a bit later. I have mentioned sanitary surveys a couple of times. If you have not seen this form, here are a couple of examples on the screen. One for a dug well and one for a river supply near a refugee camp. This form prompts you to answer questions about potential contamination risk for a water source and should also prompt actions about those risks. For example, the dug well form asks questions such as, is there a latrine within 30 meters of the well? Are there any cracks in the cement floor surrounding the well? For the river, some of the example questions are people defecating close to the river? Are people washing or bashing upstream of drinking water collection point? It is worth noting that people affected by disaster will be doing their best to take care of their need before you are likely to be up and running with any assessment and installation of equipment. If there are immediate actions such as those listed here, which can be taken to improve the situation, they should be done. If actions can be taken to improve what is currently happening while improved solutions are implemented, this will help to protect health. A suitable water site can look like this. This was taken at Samar, Philippines during Typhoon Haiyan in 2013. What makes this suitable? I'll let you think a few seconds about that. Okay, maybe it's close to the main road. Maybe the availability of flat space, gravel for drainage, etc. A few filler points to think about in water source and site selection. Don't forget about the guidance in SPHERE. In the WASH chapter, Appendix 1, there is a good checklist of assessment questions that can help if you are unsure. One of the questions you will need to answer is, do we bring the water to the people or the people to the water? How water is transported if necessary and distributed needs to be considered and can influence the site selection. If a site is selected for setting up bulk treatment, it's difficult to change, so make sure all the points contributing to the final decision have been well considered. Following from water source and site selection for bulk treatment, we will also be required to store and distribute our treated water. So now we will look in a bit more detail at this aspect of distribution. Again, coming back to sphere, we are given some guidance about the maximum distance between household and water source and maximum queuing time if people have to fill container at a common distribution point. Sometimes in large disaster, there may be a need, at least initially, to allocate times for water collection to reduce waiting. When considering how people collect water, it's important to also make sure that access for all is considered, that the elderly, people with disabilities, any marginalized groups, that all will be able to access water supply. Sphere Water Supply Standard 3 on water facility outline what we should consider in our distribution. People have adequate facilities to collect, store, and use sufficient quantities of water for drinking, cooking, and personal hygiene, and to ensure that drinking water remains safe until it is consumed. The key indicators to meet this standard. Each household has at least 2 clean water collecting containers of 10-20 liters, 1 for storage and 1 for transportation. Water collection and storage containers have narrow necks and/or covers for buckets or other safe means of storage for safe drawing and handling and are demonstrably used. There is at least 1 washing basin per 100 people and private laundering and bathing area are available for women. Enough water is made available for bathing and laundry. The distribution assessment also needs to consider that each context will need a different approach. For the distribution assessment, we need to consider the dispersion of beneficiary, the distance to the water production site, the status of any original water system and electricity connection if they were existing, the type of truck available and road condition, the water distribution areas and the warehouse in the region. Special efforts are needed to assess people in hard-to-reach locations and vulnerable groups. Pay attention also to the capacity of the affected communities. Component of the distribution response will reflect the water resources available, location of the beneficiaries, and the environmental surroundings. Onion tank on the left of the slide, below left, are really useful for holding treated water due to their rapid deployment, mobility, and durability. They need to have their covers installed if being used for treated water. If necessary, safe water will need to be transferred to locations accessible by the beneficiaries. This may require tankering, especially in the early phases, or for closer proximity pumped or gravity-fed water supply system. For local storage, Oxfam tank on the left top are an excellent medium-term option once they are established, which can take the better part of the day. Deliver water to the tap stands by gravity where available or through pumping. We also aim to provide the beneficiaries with household water storage containers. Important to see what is available in country or what's commonly used in that area. Once distributed, assuming sufficient human resources, good to observe level of usage of items distributed. Not only jerry can, bucket, but NFI in general. And please remember, no distribution without training. If items distributed are not common to those affected by a disaster, make sure there is an education awareness raising session accompanying the distribution activities. Water tankering, also known as water trucking, can be a rapid means of transporting water to areas in need during the initial phase of an emergency. The design of the trucking is critical to the efficiency of the distribution. We will always review the types of truck available, the road condition, access, distances, etc. Tankering operations, however, are expensive and relatively time-consuming to administer. So it is necessary to consider the exit strategy from the outset. Remember, tankering is much more efficient if water can be offloaded to storage tanks than allowing people to collect their water directly from the tanker. This photo to illustrate the water trucking. So the left photo is the specialized water truck. The top right photo, this is a transport bladder on the back of a standard flat tray truck. Then in this case, we have to ensure that the bladder tank is secured with the included strap, as the water will slosh around during transport. The bottom picture, this was taken at Chautara in Nepal, where standard tip trucks were used with 4 to 6 1,000-liter tanks loaded onto the back. Chlorine dosing was conducting at the source. This is a photo of an Oxfam tank. What is wrong with this picture? Nothing? Or maybe ponding which could breed mosquitoes. No drainage. An example of water distribution point. And look at this photo and think what possibly could go wrong. I leave you a few seconds to have an idea. So we can notice few things. Maybe first, children are doing all the work. Perhaps a jerry can full with water could be heavy for a young child, especially over a long walking distance. That may pose safety, security concern if water point is located away from dwelling. This container, it looks like really unhygienic containers, like high risk of contamination. Then we can see water being wasted. So if that is the case, we need to think of proper drainage or ways for runoff or seepage of water. On this photo, we can see an example of the east coast states of Malaysia that was hit by floods in 2015. At that time, the team utilized local timber to construct an elevated tank stand. This highlights one of the key characteristics that we can bring to an emergency response: the ability to be resourceful and utilize what is available locally. The tanks were sourced from the community and were used in the transition to recovery. Another example of the needs to be resourceful and adapted to our surroundings, this photo was taken during an emergency wash training organized by CVTL, so the Red Cross of Timor-Leste. The site was located next to a concrete block factory, so instead of building a timber frame as originally planned, concrete blocks were sourced and used to elevate the tank. Also, be mindful of how you can be efficient in packing up from a site. In this case, after the training was complete, the blocks were utilized in a construction project. And the Red Cross from Timor-Leste focus is the Kit 2, where we have numerous 2,000 or 2,100 liter tanks pre-positioned around the country, water bladder, onion tank, etc. So this is the end of the first part. I will give the floor to Samuel.
Very good. Okay. Hello, everyone, from Cox's Bazar in Bangladesh. I'm currently sitting in the water quality laboratory, so it comes with a good location to talk about water treatment. So now that we've discussed the raw water source, we're going to discuss how we would do the treatment for the raw water. And I just wanted to answer Victor's question in the conversation box. The question is, would the open top water bladder be covered too, and when? The raw water, to answer the question, Victor, the raw water doesn't need to be covered because it is raw water, it's untreated water. But definitely the treated water tanks, the plastic tanks and the Oxfam tanks that Ludovic described in his presentation would definitely need to be covered to ensure that the treated water remains treated. And you'll see that through this presentation. So this slide outlines key factors for water treatment process selection. In the initial stages of emergency, water must be supplied quickly, so an upgrading approach to treatment is necessary and has to be considered already from the beginning. The availability of material resources and organizational preferences often decide the solutions chosen for water supply. Such things include organizations may send in equipment, such as their own modular kits, before a thorough assessment to ensure speedy implementation phase. We often refer to those as the ERU kits, the M15 or the M40 kits. Organizations may also have modular mobile treatment kits, which are very expensive but useful in the emergency stages of emergency, especially to supply water to health centres. And organizations may prefer to use local materials, methods and skills wherever possible to benefit the local populations and to improve operation and maintenance of systems in the long term. Such examples were shown in Ludovic's recent presentation about the timber planks or the brick supports for the tanks. So whatever treatment process is selected, the general objectives are the same. There are two immediate objectives, which are to protect the water sources, to ensure minimize risk of contamination, and to provision the water of a reasonable quantity. As the medium-term objectives, we have to continue to improve both the treatment and the access. So the first 2 points are immediate objectives, and then the second 2 points are medium-term or mid-term objectives. So before we go any further, it'll be useful to define a few of the water quality parameters that we are commonly discussing when it comes to water treatment. First one is conductivity, which is a measure of how salty the water is. And this can be a particular issue in regions that are close to the ocean. Most of our standard water treatment equipment does not deal with salinity sources. So salinity or conductivity should be checked to see if they meet the requirements. If we have conductivity that is between 0 or 1000 or 1500 microsiemens per centimeter, people usually cannot taste this, so it's not a unadvisable. It's not rejected because of the acceptance from users. Turbidity is the measure of particles in the water, and we want these to be less than 5 NTU. This basically, and we'll discuss a little bit later in the presentation, is the color, sort of the look of the color of the water. pH, again, similar to turbidity and conductivity, is not a health-based target, but having the correct pH will impact the functionality of our equipment. Fecal coliforms, also called thermotolerant coliforms, which should be less than 10 coliform units or CFU per 100 milliliters. Free residual chlorine or free chlorine is when we are disinfecting with chlorine, we want to have at least 0.2 milligrams per litre, as Ludovic mentioned. And then the last point is the colour and the odour and the taste need to be acceptable for some uses. And this will depend different locations, different countries. So here we have some pictures of various water quality testing equipment. We have a mixture of manual testing as well as digital testing. On the top left you have a pool tester, which is testing for pH as well as free residual chlorine. On the bottom left you have a digital pH meter. In the middle you have a conductivity meter, a digital conductivity meter, which is measuring the salinity. The top right is a full kit. It's a field lab kit. It's a field kit, and it can test all different parameters. The far right, you can see compartment bag tests, which are testing for E. coli. And then the circle is also an E. coli test, a fecal coliform test, which is identifying identifying fecal coliforms that you can see in the, I think it's the yellow, and total coliforms, which are in the red. So in order to meet our desired water quality treatments, we treat water in three main processes: sedimentation, filtration, and disinfection. So sedimentation is allowing the dirt to fall to the bottom of the container, and sometimes this can be done physically or it can be done chemically. Filtration is the removal of dirt by passing through a filter, such as a ceramic or sand. And then disinfection is to ensure that there are no remaining disease-causing germs. And this usually is done by chemicals such as chlorine, heat, and even sunlight, such as UV. So let's start by considering the removal of solids by processes of sedimentation and filtration. Have a look at this photo and think about what are you seeing in this photo? What do you think is happening in this photo? So what I'm seeing is that inside the blue bucket we have sediment has been reduced or flocculated into the bottom of the bucket, and then that water is being poured and filtered through a cloth into the green bucket. The solids that you see at the bottom of the blue bucket, these could be organic, such as algae, which are found in lakes, or it could be inorganic, so things like silt and clay and sand. So turbidity, as you mentioned, turbidity is sort of the color or the cloudiness or the haziness of a fluid. And it's caused by a large number of particles that are invisible to our eyes, but basically they float in the water. So high turbidity affects the effectiveness of chlorination. So when there's high levels of sand or organic, such as algae, they absorb the chlorine and it doesn't kill the germs inside the water. So we need to remove the turbidity first so that the chlorination process works more effectively. Such methods include sedimentation, coagulation, flocculation, and filtration. So in the previous slide, we saw sediment had joined together and coagulated, and then had dropped to the bottom of the bucket. And the little diagrams that you can see at the bottom, the little tubes, is sort of a representation of what turbidity is. So On the far left, you've got 250 NTU, would be high levels of turbidity, high levels of sediment inside floating inside the water column. And then on the far left, you see 10 NTU. So how do we measure turbidity? Well, we can do it both manually and digitally. The most simple method is the one that you see on the left-hand side, which is using a graduated turbidity tube. And then the one on the right-hand side is a digital turbidity meter that you would more likely use inside a laboratory. The one on the left, the turbidity tube, is more of a field-based measurement. The digital meter on the right-hand side, these meters pass light through a sample of water that measures how much light is being scattered by the particles that are present. And from this light scattering, they can calculate the level of turbidity. So the turbidity tube, a very simple item to carry into the field. It requires no consumables like tablets or anything like that, and becomes very easy to use. So what we would do is put the water into the turbidity tube, as you see, and you slowly fill up, and the little disc that is sitting at the bottom of the turbidity tube, when you can no longer see this disc, such as at number 7, then you would stop, and then you would measure the level of turbidity, and you would measure it on the side of the turbidity tube. So how would we decrease turbidity? Sedimentation or settling is the main process, and this allows for particles to sink to the bottom of a tank, and water is removed from the top of the tank. So the clean water is taken off the top of the tank, while the sediment and the dirty water remains at the bottom of the tank. Sedimentation on its own can take time, or in the case of very small particles, they will remain suspended. So silt and clay particles can remain suspended almost indefinitely. So sometimes we carry out coagulation-flocculation to enhance and speed up the sedimentation of particles. Filtration is another option of removing particles. In bulk water treatment, this is usually done with a sound filter or membrane filters, and these processes can be enhanced by also using coagulation and flocculation, so they can go together. Coagulation and flocculation is a water treatment technique where we add chemicals such as aluminium sulfate, or in the PowerPoint presentation you can see what's called alum at the top of the tank there. So aluminium sulfate, or you can also use another chemical called ferric chloride, which basically allows the particles to stick together so they become larger and heavier, and will therefore sink in the sedimentation and be trapped in the filtration processes. When these chemicals are added, it is important that they undergo rapid mixing, and there is sufficient time given for the flocculated particles to grow by gathering up the fine particles in the water. To work out the dosing rates of chemicals for coagulation and flocculation, we usually perform a series of dosing experiments known as jar tests. We want to optimize the dose to get the best settling with the minimum amount of chemical, not only to keep the costs at a minimum, but also to avoid the carryover of aluminium or iron into the treated water. To do this effectively, we use a process called jar tests, and it is important to have make sure we have clean tools, such as stirring sticks, jars, buckets, and syringes, so they give us the correct result. If testing for a source from a tap, we should try and let the source run for some time in order to that we get the correct water sample. If taking from a pond or a lake, we also want to try to take from the middle or away from the edge of the lake where particular sediment or buildup can sort of give us a false result. So this is the step 1 and step 2 of the jar test. So in order to do this, initially we would make a mother solution. So that's step 1, is to make a mother solution, and we would dissolve 10 grams of granular alum in 1 litre of clean water, and that creates what we call a 1% mother solution. We then pour a certain amount of the mother solution into 1 litre jars with water, with 1 litre of water in each, and we would have a series of these jars lined up. So you can see here in the presentation we have 6 jars, and we would add into the first jar 5 millilitres of the mother solution, and in the second jar 6 millilitres. The last jar we would add 16 millilitres of the mother solution. So step 3, we want to mix this rapidly to make sure that the coagulant is dispersed throughout the jar and it's not concentrated in only one area, for example at the top, but we would want to mix it so it is evenly dispersed. Step 4 is flocculation, so stirring slowly and encouraging that the sediment comes together, and it creates what we call flocks. So if you remember back to that blue bucket, you saw these groups of sediment, and that's what we call flocks, and they help to form, and then they become heavy, and then they sink. And that's step 5, is allowing those flocks to sink and settle. So in order to, then we would measure the turbidity, step 6, and results can be plotted on a graph to determine the optimal dosing rate. We can repeat this test because jar testing is not a once-off, especially for surface water, which is usually changing often. Jar tests should be repeated regularly, and dosing is adjusted to ensure that we get the right results for the raw water that we're using. So an example would be when a big rain comes through, it might increase the amount of sediment that has come into the surface water because of the runoff from the land. Therefore, we may need to increase the amount of alum that we're using because of the increased amount of sediment in our water source. In step 9, we want to test the pH of the raw water as well as the final product to determine if pH adjustment is necessary. So the optimum pH for alum is 6.5 to 7.5. So outside that range it doesn't work as well, so we may need to consider adding other chemicals to try and change the pH of the water before adding the flocculant, before adding the alum. So how do we do the calculation? So we've made the mother solution. We have 10 grams of in 1 litre of the mother solution, and then in this example that you see here, it was determined that the 16 milliliters of the alum mother solution created the best result. Now what we want to do in this solution is how do we scale that up to the tank, to the big tank size that we're using, and this is the calculation that we would use. So on the bottom, you see at the bottom, you would do 10 grams per 1000 milliliters. This is the mother solution, multiplied by 16 milliliters of the mother solution over 1 litre, the size of the jar test, and then multiplied by the total volume. And in this example, the total volume would be a 15,000 litre tank. So by using this calculation for this example, the outcome is 2.4 kilograms of alum is required to be added to a 15,000 litre raw water tank to effectively reduce or remove the sediment in the water. Disinfection. So the other main important treatment process we used after having removed the particles is disinfection. We can use disinfection to kill pathogens or disease causing microorganisms in the water. We can't see these microorganisms. Bacteria is 0.3 microns, for example, whereas viruses can be 0.005 microns. As a comparison, a human hair is in the order of 100 microns in diameter. So bacteria and viruses are in the equivalent of 3 to 8 times magnitude size difference than a human hair. So it's not possible to see these microorganisms. Chlorine is the most common disinfectant used, as it is effective against a wide range of pathogens and can also leave a residual disinfection capacity inside the distributed water. There are other methods of disinfection like heat and ultraviolet radiation, as well as other chemicals like ozone and chloramine. In bulk water treatment in emergencies, we almost always using chlorine as the disinfectant of choice. As with the jar tests for coagulants, for chlorine dosing we also need to do a small-scale test to work out how much to dose. This we call a bucket test. The purpose of the bucket test is to find out how much chlorine we need to add to clear water so that there is 0.5 milligrams per litre of free residual chlorine after 30 minutes of contact time. So the jar test, which was the sedimentation process, used a 1 litre jar, and the bucket test, which is the chlorine process, uses a 10 litre bucket. So again, it's a similar strategy that you would use for the sedimentation for the alum. You would line up a number of buckets, you would create a mother solution, and then you would add small amounts of the mother solution to the multiple buckets. You would mix or stir for 10 minutes and then leave to react with chlorine for 30 minutes. And this is quite important. We must remember to wait 30 minutes after we do the mixing in order for the chlorine to effectively react with all the microorganisms. We would then measure after 30 minutes and we would determine the best amount of mother solution added to those buckets. And again, we want to have 0.5 milligrams per litre is the preferred item. So the formula for the bucket test is very similar to what we did for the sedimentation test, for the jar test. What we must remember here is that each chlorine has a percentage. So often we refer to a concentration of chlorine, and in this example we're using a 50% concentration. Chlorine varies. Often the range is between 50 or 70% concentration of chlorine. So instead of, so the calculation at the bottom left, you see 20 grams per 1,000 milliliters, which is the mother solution. So the reason we get 20 grams is because of the 50% concentration. So it doubles the amount of grams that you would need. So you multiply this by the test result, and the optimal test result was 1.5 milliliters in a 10-liter bucket, and then you would multiply that by the volume of the tank, or how much water you were treating. So in this example, using a 50% chlorine concentration, you would use 24 grams for an 8,000 litre tank. So in summary, when we are talking about bulk water treatment, this is the overall schematic that you will find in the ERU M40. Coagulation and flocculation for sedimentation, followed by disinfection. And so the site selection that you see on the left is what Ludovic talked about, as well as the distribution Ludovic talked about. So in step 2 is the sedimentation, where we would do a jar test to ensure we have the correct amount of alum or chemical. And then in number 3, we would do a bucket test for the disinfection when we use chlorine. This is an example of a packaged water treatment plant. That is one of the options used as part of the ERU M15. So this aims to treat enough water for 15,000 people, which uses coagulation and flocculation to aid filtration. And you see on the left-hand side is the flocculation tank. And then water is disinfected also with chlorine, and you see that on the right-hand side. Here you can see and this is from the other side of the water treatment plant, where you can see dosage pumps for the chlorine, as well as the carbon filter for the filter for the filtration of the water. A final note on the packaged treatment unit is that they are equipped to deal with normal surface waters. They're not equipped to deal with salt water or highly polluted sources. This is the same for the standard chemical bulk treatment process that we looked at before with step 1, step 2, step 3, and step 4. So what we need to know, and what Ludovic presented in his slide, is making sure that we select the right source before we can do the correct treatment process. So that brings us to the end of this week. We'll take some questions now, and then Ludovic will explain to you the following process.
Thank you very much, Samuel. So you can write your question in the chat box. I will just come back to the first question of Victor, because I can say hello to Victor at the same time. Be careful when we use the term, because usually bladders, when we're talking about bladders actually is the water pillow, let's say the water pillow technical term. So this is the one we saw on the photo in Philippines. So it's flat and it's closed. So usually this one is only for treated water. The other one, it's what we call onion tank or the Oxfam tank. They are open on the top. So it will make, so you can have the choice to cover or not cover. So if it's raw water, we don't need necessarily to cover it. But if it's treated water, we will cover it. Just for the raw water, because of the raw water, we are doing the sedimentation process, as Samuel explained. We will have to clean inside, so this will not be possible in the bladder. So that's why usually we are making sedimentation in the bigger tank and these tanks, they are often open on the top to allow a better cleaning, a faster cleaning. The second question, conductivity about 2,500 means that is not feasible for treatment. Today we have mentioned the treatment unit which are not desalinization unit. So outside this kind of unit, all the other, they will not affect the conductivity or the salinity of the water. So if you have a salinity of conductivity of 2,500 before the treatment, you will have a conductivity of 2,500 after the treatment. Meaning, if it's a salty water that people, they will not drink after the treatment, even it's safe water without bacteria and so on, the people, they will not drink it because it's still salty. Do we have other questions? Yeah, conductivity refers to all minerals we can have in the water. So, like for example, if you talk about mineral water in Europe, a lot of people are drinking mineral water. There is high conductivity because there is high mineral like magnesium, calcium, and so on. For us, often is the issue related to sodium, chlorine of sodium, so the salt. But yes, it refers to presence of all the other as well. Okay, so if we don't have more questions now, that's okay. You can have questions later. You have our contact, so feel free to send any question. We will answer and we will add in the website. We have one more. Yes, that's a very good question. The draft, that's one particular situation. We have another situation that I think Samuel know well as well, is the Pacific Island, where sometimes you don't have a lot of fresh water. So this is like drought is a specific disaster, slow onset disaster. So this is really something we need to work on preparedness. And in this case, except doing long water trucking and a big emphasis about the use and the preservation of water, that's the solution we will have in such case. So we mentioned at the beginning the number of liters per person per day. So in such context, we can go to the lower limit and really work on the preservation of existing water, existing source, protection of rainwater harvesting, and so on. Should all water used for domestic purpose be treated? Like in a context of emergency, like floods, or in many places, you will need to have access to clean water, to safe water. we have mentioned, I think last time, sorry, that also for hygiene practices you need clean water, because then you will have impact on health as well. So that's why when we are doing the water treatment, we are including as well the domestic use, because yes, for hygiene it's very important.
I might jump in there and add something, Ludovic, if that's okay.
Yeah.
So where we are currently working in Cox's Bazar, working on the population movement operation from displaced communities from Myanmar, we don't have any surface water sources, so we're using a lot of groundwater. Groundwater does take time to develop and to develop properly, and also there is big concern that if we don't treat with it correctly, that it can be mismanaged. But there's only a certain amount of water that we can treat per day, based on the size of the boreholes, based on the aquifer, based on the size of the pumps, the size of the tanks, etc. So what we have done is to undertake community engagement processes to try and educate, inform, and create behavior change within the community to ensure that, as you have suggested with the drought purposes and the domestic purposes, that the treated water is used for consumption purposes. So for their health issues, those that, for example, drinking water, water that you use to cook and clean your food, water that you use to clean your hands, water that is being used for, say, cleaning your clothes, or water that is used for cleaning your latrine or toilet. These are water that the priority or the risk of health issues is much lower, and you could use potentially untreated water for those purposes. So it'll come down to how much water you have, how much water you can treat, and what is your priority in terms of what you need to invest the healthy, or what you need to allocate the treated water towards.
Thank you, Samuel. Next question, is there any water treatment solution for nuclear disaster preparedness and response? Not on my knowledge. I know that WHO just launched last year a specific guideline about water in such disaster. When deployed, are these tools to assess and access the groundwater table? So I can let Samuel talk about that, if you want, Samuel.
Yeah, so thanks, Ludovic. So there are tools that we can use to measure the groundwater level. Usually the most common one is called a water level dip meter, which is basically a sensor that is on a tape measure, and it's lowered into a borehole. That can then, when the sensor hits the water, it beeps, and you can measure the distance or the depth of the sensor. And we use this often when we're doing pumping tests as well, to help with the assessment of the aquifer. The second type of material that is used is called a data logger, which is an automatic measurement, and it usually is lowered into a borehole below the water level, and it measures the pressure of the water level. And so pressure is related to the height of the water level, so it can calculate the height above the data logger. So at a particular time, then you can pull that data logger out connect it to your computer and download the data from the data logger. To go beyond that, when you're doing groundwater, you would have to do groundwater pumping tests, which measure the drawdown of a groundwater level. However, what you then need to think about is what are the other impacts, so what are the other boreholes within your vicinity that are also extracting water from the groundwater, extracting water from the aquifer. And there's an impact with regards to rainwater and how much the aquifer is being recharged. And so this is a much higher level of analysis and much higher skill level when we include people such as hydrogeologists who can model the groundwater and model what the safe yield of an aquifer is, how much water is allowed to be extracted from the aquifer before there becomes problems with the aquifer, such as saline intrusion. So that's when salt can come into the aquifer and then it can destroy the aquifer, and it does not become fresh anymore. So that's a much higher level. It's definitely what we're dealing with in Cox's Bazar at the moment, where we have a lot of groundwater pumping. And I've just come back from a meeting this morning which was discussing how we're managing that, the modelling that we're doing, the data that's needed to be collected in order to correctly calculate what that is. So it's actually a very tricky question, and obviously we would want to know what the aquifer is before we start pumping from it, but in an emergency situation, sometimes that's not possible. Sometimes we start pumping and we have to work backwards to try and understand what the aquifer properties are. But it's a very tricky question.
So it's raised the importance of having information in the area you are going by secondary data, by hydrogeology report, existing network, existing borehole, the depth, the size, the yield. So all the information you can collect will help you also for the decision. And for sure, all what Samuel had mentioned will not be necessary what you will do in the first week of your arrival in the situation.
Sure. The question about WASH committees?
Yes.
So again, I think this is important to understand, as is quite well mentioned here by Aga, as to who are the change agents and who are the mediators. So for WASH committees, for communities that are not displaced, I think it's much easier because they maintain their cultural context and cultural ways of dealing and with certain issues. In some instances, such as refugee camps or also internally displaced camps, sometimes this becomes much more difficult because the context, the social context in which you are working is not the same as what it would be back in somebody's hometown. So this is much more difficult to manage. Definitely we would want to identify leaders in the community, be that they have a formal role or be that they are well respected sort of informally from the community, definitely as change agents to make those decisions. Decisions, however, need to be made based on evidence, based on data. So for the groundwater example, for example, without knowing what the aquifer is, we cannot say what we should be doing because we don't have sufficient information, evidence or data that would lead to making effective decisions. It is difficult, the last point Aga is making, is it difficult to reach each and every person. Yes, that is one of the challenges that we face. Another challenge that we face is to make sure that everybody has an equitable amount and equitable quality of water. So we may be reaching everybody, but some people are getting more or some people are getting less quality and quantity of water. And that's the tricky part. And again, as Ludovic said, it might not be straight away, but over time you try and expand that. And so water supply needs to be very much linked in with the community engagement and our hygiene promotion approaches, so that we are understanding from the community who has better and who has less, and so we can adjust adequately to ensure that everybody has equitable amounts.
Thanks a lot, Samuel.